Hello, and welcome back to Data Science Castnet. In today's video, we're going to be taking a look at the ADDi Alzheimer's Detection Challenge on AI Crowd. You may have seen this competition but been hesitant to join. My hope is that this video will convince you to give it a shot. So a bit of brief background. The clock drawing test is a quick way to assess cognitive impairment. Patients are asked to draw a clock showing a specific time. I found these examples online. You can see that for some patients this is an extremely hard task. I'm not sure how ADDi would have scored. So these images are medical data and therefore very sensitive. Rather than providing us with the actual imagery, the competition organizers have extracted specific features from the images and made them available as a table of data. And even then you can't download it, you're restricted to accessing it through a special cloud workspace they've set up. More on that in a bit. So the goal is to create a model that can go from these features to a prediction about the patients, assigning them to one of three classes: normal, pre-Alzheimer's, or post-Alzheimer's. Among the many features we're given are things like which digits are missing, how far they are from the center, how much area each digit covers, the average angle between digits and the variance of that, the angles of the minute and hour hands and their proximity to the digits that would constitute the correct time, measures of how round the circle is, and so on. 120 features in total. From these, we can draw approximations of the clocks to get a better idea of the data. Here are a collection of images generated from the normal class, and here are some from the post-Alzheimer's class. You can see that the difference is usually fairly stark, although even some of the normal images are quite strange. Things get more difficult when we look at the pre-Alzheimer's class. Many of these are difficult to distinguish from the normal ones. We'll see later that the models also have a hard time distinguishing between these two classes. Enough background, let's see what a minimal entry might look like. So as I mentioned, the sensitive nature of the data means that we restrict it to working in this cloud environment. It takes a little bit of time to set it up, but once you have it, you're presented with this kind of cloud space where you can access essentially a virtual computer on the cloud. When you start it up and click desktop, you're greeted with effectively a remote view of the desktop of this computer. But it's quite easy to launch different applications. So for example, you could launch Terminal Emulator, type in Jupyter Lab, and get the sort of familiar Jupyter Lab interface. So I'd recommend, rather than starting from scratch, looking at the notebooks that the community have made. There's a few different starter ones. And these are useful just because they give you all the setup that you need in terms of loading the data, creating submissions, and so on. So all of that logistics is taken care of. So based on that, whatever model you choose, it needs to be able to assign probabilities that a given sample belongs to each of the three classes. A first attempt might look something like this: training a random forest classifier and using the predict proba method to get the aforementioned probabilities. Give this a go and see how you do, although fair warning, it won't score very well. You see, there's one big thing that we need to take into account with this competition. The training data has a different class balance to the test set. This means that if we train a model with the training data as is, it will predict the normal class with a high probability that won't line up with the prevalence of that class in the test set. The simplest solution is to try to rebalance the training data so that it more closely resembles the test set. But beyond that, I have a whole notebook full of different suggestions to combat this that you can check out. It's in the Notebooks tab on the competition. I can't emphasize how important this is. Like just adjusting these class weights was the difference between 50th place and 15th place. So no other changes to the model or models that I was using, just tweaking that balancing strategy made a huge difference in terms of position on the leaderboard. Okay, so assuming you've dealt with the balance issue, the next phase is to find other ways to improve your predictions. It's kind of easy to get carried away here, spinning up dozens of notebooks to try different things and relying on your leaderboard score to see what works, and I'm guilty of this. But my advice is to spend a little bit of time on infrastructure, and you'll definitely thank yourself later. So I've set mine up so that I can create a model configuration, basically just a dictionary that specifies the model type and parameters, as well as the balancing strategy, feature engineering steps, and so on. We can then compare different configurations, taking the average score over many different splits, to properly explore whether a particular change is actually leading to an improvement, or just happen to coincide with a lucky split. So the thing with competitions like this is that the final solutions that people arrive with are often all sort of doing just about as good as it can possibly be done. So the difference between sort of 3rd place and 20th place is in the 3rd decimal point. It's really, really small. So I actually often get kind of bored at this final stage where everyone's fairly close, you're all like nearly there, and it's now just this hard work of tweaking and refining and tweaking and refining and finding anything that can give you that slight edge. So that's not the fun part for me, but I am actually kind of keen to try it for this one. And if you are too, I know that it's just down to putting in that hard work to find all of those 0.1% improvements that you can make. So if that's you, good luck, happy modeling. And yeah, I hope this has inspired someone to give this a bash. Cheers for now.